I'm from the Vrije University in Amsterdam, and I'm going to talk about work I did jointly with Teodor Crivat and Herbert and Andy Tanenbaum. And our topic is the problem of Socket API and the system calls and how to improve on that. So the Socket API is de facto the standard API to build networking applications, and it's a well-understood API because it's been here for decades, and it's being taught at every networking 101 course at the universities around the globe. And for those reasons, also all the legacy software is primarily using this API. The good thing for that is also that virtually every operating system implements this API, which makes the application portable across the platforms. However, this API is also problematic. The key problem is that each of the API calls is in the commodity operating systems implemented as a system calls, and as has been demonstrated in the past, system calls are disruptive because the application has to switch the execution into the operating system. I consider here a monolithic kernel like Linux or Windows. So effectively the application is paused for a while the operating system is running. And the execution of the operating system interleaves the execution of the applications. And many applications use non-blocking system calls just to try whether something is possible, and this trip to the kernel and back is expensive in case that the application doesn't get anything back. So the widely accepted solution to the API problem is to come up with new API. So everybody who is doing high performance networking tries to invent some new API, which are not standardized, and that breaks compatibility and breaks portability across the platforms. And the legacy software cannot benefit directly without code changes from the advances in the performance. Typically what changes in the new API is that they relax some of the constraints put on the API by POSIX. And once the applications that do not need all the bells and whistles of the POSIX API, if we take out the constraints, we can implement the new interfaces in a faster way. We can also batch the system calls together, which amortizes the cost of the system call, but for that, we effectively need to have multi-threaded applications, so we have something to batch. And these new APIs also need some non-standard way of talking between the application and the operating system kernel. And the kernel then polls these sort of channels, and to poll them, we need to set some timers and thresholds. For instance, how many system calls we batch together before we send it over to the operating system, or when should we make a system call if we cannot gather enough system calls at once. And getting the right values for these knobs is not straightforward. So we do not believe that the Socket API is so broken, but we think that the implementation in the commodity operating system is not as good as it can be. The key problem here is the system call itself. It's a synchronous transfer between the execution of the application into the operating system, during which the CPU switches the stacks, page tables, instruction pointers, and also the operating system has to execute some code to save and restore the application context. So while we're swapping these streams of execution, the internal structures of the CPUs are being thrashed, which has an impact on the application performance in terms of CPU per cycle, instruction per cycle ratio. That's been demonstrated in the past, and it takes some time for the application to recover the full performance, by which time the application makes yet another system call and everything is broken up again. The high-performance application, networking application nowadays typically use the event-driven model, which means that we have a single thread of execution on each core, so it's also hard to batch system calls. And each thread runs a main loop on its core, at the top of which it monitors the activity in sockets, but some of the sockets are ready. And if we have a busy application, we kind of know that some of the sockets will be ready when we test, but we don't know which of the sockets and we don't know how many. For that, we have to ask the operating system. And once we know which of the sockets are ready, we carry out some action determined by the state machine of the application. So we have to be able to test the state of the sockets efficiently. If you look at some of the actions that the servers typically do, here for instance, we know that there's a listening socket, it's ready so we can accept a connection. But we don't know how many connections are there, so the application typically in a tight loop tries to accept several connections, and the application traps into the operating system, gets a connection, but while the execution returns into the application again, it immediately goes into the operating system. So we're losing quite a few cycles here, which we could use on processing the client's requests, and it increases the latency of processing. And at some point, we made a call, and there's no more connection to be accepted, so we lose cycles without actually getting anything. Also, the application usually immediately tries to fetch some data from the socket without knowing whether the data are ready or not. So there's a pure speculation here. So the challenge for us is to remove the system calls from the API, but we want to keep the API intact so the legacy applications can benefit. So here's the idea. What would happen if the application can see what is in the socket buffers, what's the state? In that case, the library that implements the socket calls can easily resolve many of the system calls already in the user space, and failing the non-blocking system calls is almost free. And the application can read and write the data directly to the socket buffers. And we would only use the system calls to block the application if there is no work to do. In that case, taking the penalty hit is acceptable because there is no work to do. So what we propose is what we call exposed socket buffers. Basically, each socket is represented by a piece of shared memory between the application and the network stack of the operating system. And that piece of memory, we implement two unidirectional queues that allow us to ship data between the application and the operating system in a lockless manner. If we implement the socket this way, the application can easily test whether the socket is empty when we reading data or accepting connections. As well, it can test whether it's full when we try to write. And the applications also often query the system how much data are actually in the socket so that the application can allocate appropriately sized buffer when it's receiving the data. And you can do this in user space. So we go back to that example of accepting connections. The application can go and accept the connections in user space as long as it sees that there are some connections. And at the end, the failed socket call is basically free, it's very cheap. So, but how do the application and the operating system communicate with each other if there are no system calls? Well, obviously the application can poll. The event-driven model is designed around polling. So the application or the library that implements the system calls basically sweeps across the sockets that the application is interested in, and if it sees that some of the socket is ready, it returns those sockets to the application. And only if this user space test fails, the application executes some sort of select-like call of your choice, basically, to block and tell the operating system that it's interested in some activity. Also, we can implement all the blocking calls like reads and writes in non-blocking fashion. And we only use the select mechanism to monitor this one specific socket. So the operating system knows that the application is interested in something, and once the new work arrives, the operating system can go and wake up the application. The application does this polling on its own quantum, but for the operating system and the network stack to poll, we would have to introduce some dedicated threads that would do that, because normally in the operating system would run on behalf of the application when it makes a system call or because of an external event. And these dedicated threads, that would interleave with the execution of the applications, and this is exactly what we want to avoid. So what if we place the network stack on a different core than where the applications are running? Then the network stack can easily poll with no interleaving and no interference with the applications. And it doesn't even have to poll all the time. It only needs to check the sockets if it sees some activity from the application. But how does the application signal the activity to the network stack? Well, it can set some flag, some mark somewhere in memory, which the operating system is checking. And on x86, we can use efficiently the env instruction, which just can hold the CPU and wait for a memory write. And so the application can constantly set this flag, and if the operating system is not actively polling it, wakes up, and this is fairly efficient communication across the cores and in user space. So because we have the exposed socket buffers, we have to also map them between the application and the operating system. And the operating system does it before the application, of course, gets the handle of the socket. But constantly creating the mappings, that's not efficient, that's slow. But if we have an application that is busy and there are new connections being opened and closed all the time, we don't have to tear down these mappings every time we close a connection. We can simply recycle those mappings. And we're using these mappings in user space. This is fast. Of course, it can happen that at some point we have many unused memory mappings, but the operating system can decide and reclaim them, and it can do them in a batch. So to summarize, we do not really need system calls for reading and writing from the socket, for polling and checking the sockets, and for signaling from the application to the operating system. In addition, using the exposed socket buffers, the application can pretty much copy data from its internal private buffers into the socket buffers, and the operating system doesn't have to make expensive copies across the memory protection boundaries. Also, if we map the socket buffers in a good way, the operating system doesn't have to copy the data further and can transmit directly from those buffers. And as I mentioned already, we only use the operating system to block the application. So here's the question: does it really work? We've implemented a proof of concept in an operating system we call NewtOS. We're using it as a research vehicle, and we use it in our previous work. It's based on Minix 3 multi-server system. And multi-server systems are systems where the functions of the operating system are implemented by isolated processes in user space. It's just some interesting reliability properties, like that if there is some fault in the system, it's contained within these isolated processes. But these operating systems are found primarily where well, not primarily, only where the reliability is extremely important, and they are not widespread because people think that their low performance is inherent to the operating system design. But is it really inherent? And this is what we try to answer here. So in NewtOS, the network stack is entirely implemented in user space, including the device drivers. And when an application wants to make a system call, it has to send a message to the operating system using the microkernel. And that may trigger a cascade of other messages within the operating system. And all the processes that have to process those messages, they interleave with each other and with the applications if we run on a single core. But the multi-server systems are pretty good in embracing multi-core processes, and it's really easy to pick a piece of operating system because it's isolated and pin it to its own core. And this is exactly what we need if we want to implement the file sockets the way I just described. In fact, the network stack in NewtOS is not just a single user space process, it's a whole collection of processes. The figure shows just the processes we use for TCP evaluation in the test I will show. But there are more processes like UDP or packet filler. So when an application wants to make a system call, it has to send a message to a syscall server, which dispatches those messages internally in the operating system to the server that can handle that message. In our previous work, we've demonstrated that we can do that efficiently in user space, and basically the sockets we are proposing here are just a natural extension of this user space communication from the operating system to the applications. Here's denoted by the green arrow. In fact, when the system is busy and the sockets are set up, the application doesn't have to send the message to the kernel bypassing the expensive messaging. And it also can bypass the syscall server and talks directly to that server that can actually handle its system call. So just to give you some impression how messaging and how system calls are expensive in multi-server systems, we've made a test which in a loop executes a non-blocking system call that tries to receive data from a socket, but there are no data available, so it fails. In NewtOS, we have to go from the application to the syscall server and to the TCP or UDP server, crossing three processes on 3 different cores. And when you are using purely kernel-based messaging, the round trip can take as much as 80,000 cycles. So when we previously removed the kernel-based messaging from within the operating system, we reduced the cost to 20,000 cycles. But this is still huge in comparison to Linux. If you run the same test on Linux, we can achieve that in 500 cycles, less than 500 cycles. But note here that here the loop runs on a single core, has very little code that runs in the user space and very little code that runs in the kernel. So this is pretty well cached. So can we do better if we don't make system calls in our operating system? Basically, the library can figure out in user space that there are no data. So it returns immediately, and it only costs us 140 cycles, which is a huge improvement to what we had before. So we've evaluated our system on a 12-core AMD 1.9 gigahertz. We were using 10 gigabit Intel network card, and we were using the Lite web server. We were running a single instance of that web server, and we were serving static files cached in memory to isolate the performance of networking and avoid interference with other parts of the operating system. So in our first test, the clients were querying the web server for a tiny file once per connection. So here, sending the data takes little time compared to managing the connection. Our baseline is NewtOS using the legacy system call-based network sockets. And the throughput of the system is roughly 5,000 requests per second. At the same time, Linux can do about 11,000 requests per second. So using the fast sockets which we are proposing here, it helped us to boost the performance of our system, basically where the performance of Linux is. Note here that we have this slow start, when we have only a few connections, simultaneous connections. And that's because we can take the full advantage of our user space communication only when the wheels are spinning, when the system is under load. Of course, we can let the operating system poll constantly, but that wouldn't be efficient. In the next test, we request the same file, but we use a persistent connection to request the file 10 times per connection. And in this test, the throughput of the system doubles, and so it doubles for Linux. But when we're using the fast socket, it shoots up to 45,000 requests per second. Here we really take a huge advantage of not switching between the operating system and the application. And we can see the similar picture in other tests. Here we requesting 11 kilobyte file or half a megabyte file. So we can see that across the range of small requests to bulk transfers. Well, we do not only benefit from the fact that we are not using system calls, we also benefit from the fact that we actually run the application on a different core than the network stack, so they do not have to compete with each other. In Linux, the application cannot run as smoothly as in our system. Basically, we show here that the application experiences instruction cache miss ratio of 8.5%. If you run the same application in NewtOS, but we're using the legacy sockets, it's already smaller. It's 4.5 only. And without the system calls, when the application is busy and doesn't block on the operating system, it drops to 1.5%. Eventually, we have to, sometimes we still block. but it shows that the application can run really smoothly. But there are some limitations in our system as well. For instance, we can't handle fork. The problem here is that each socket is just a piece of shared memory. And after fork, the socket is shared between the parent and child, and we can't tolerate that two independent processes access the shared memory in some unrestricted way. So when fork happens, we basically revert to using legacy sockets, and operating system is responsible for the synchronization. It looks like a major problem, but fork is already pretty expensive, and if we spawn a process for handling each short-lived connection, then the fork basically outweighs the benefits of having fast sockets. We could use ioctl to work around that, somehow telling the system that the newly accepted connection is valid only in the child and not in the parent. But that would require some changes in the code of the application. But for event-driven servers, you basically do not need to change the code at all. Well, we are definitely not the first ones to try to tackle this problem. There have been a proposal by FlexiC for a general mechanism in Linux how to avoid or at least reduce system calls by batching them together. Recently, Megapipe showed also the benefit of reducing system calls by batching and by relaxing some of the constraints of the Socket API. And IsoStack was one of the projects that pioneered running a network stack on a dedicated core in a monolithic system. But the primary reason for that was to avoid contention on the internal data structures of the network stack, while the applications are still talking to the operating system using system calls. So to conclude, running the network stack on a different core and having the exposed socket buffers allow us to avoid more than 99% of system calls when the application experiences high load. Some details on this 99% are in the paper. And we can do that because the application can read information directly from the socket. And the applications typically use non-blocking system calls. The only blocking call in an event-driven application is basically select. When we can read the data from the socket, the speculative non-blocking API becomes relatively cheap. And the execution of the application and the operating system doesn't interleave, which contributes to smoother execution of both. And most importantly, we have demonstrated that reliable multi-server systems, which were always considered to be terribly slow, can actually have network performance competitive with commodity operating systems. Thank you for your attention, and I'm happy to take your questions.
So this is Junior from Universität. Your work is very interesting because recently we were also doing something like inter-sys comparison on the sockets. We found the big potential on sockets to do the sys comparison. So our work are some kind of related. So my question is, if you program the sockets without sys calls, you need to change the programming model, right? I want to ask, how much more effort do you need to take to programming under the new programming model?
We're not changing the programming model per se. Basically, the legacy applications can directly use and benefit from the improvement. We do not have to, in Lite, and we also conducted some tests with Memcached, we haven't changed a single line of code. But of course, you can change the model as well. Mm-hmm. Probably, I can imagine that you wouldn't have a single poll or select call, but you would do it on more fine-grained fashion that the application would administrate on its own because it can do the test.
Okay, thank you.
Hi, John Stallworth. I wanted to ask you what happens when you have big reads.
Big reads in like lots of, like a bulk transfers, lots of data.
Not lots of reads. Reads that are very large, megabyte reads, 10 megabyte reads. Because it would seem that your caching would get affected, the shared memory would be an issue. There seems to be a number of issues there.
True. It really depends on what the application is doing, right? How does it use the data? If it just processes data right away in the socket buffer, you need to get the data from the network device to the application.
Did you look at that issue at all?
Not exactly. We were looking at like scaling to many sockets. So we have lots of we're testing different sockets, lots of different sockets, and it doesn't seem to be a big problem. But we may experience some problem if with extreme values.
Thank you.
Nice talk.
Thank you.
I have a couple of questions. First one is that, how about running multiple multi-thread applications? For example, 2 memcached servers. Can you comment on that?
This is possible. There are basically 2 problems. The listening socket itself, if it's shared between the threads or not. And I think in memcached is used by a single thread only. But there's been previous work on how to partition the listening socket. So we can technically have internally multiple such sockets going to different threads. And the other thing is if 2 threads are accessing the same socket. There may be collision, but then the application or the library has to synchronize. But I do not think that this is a common way of writing applications, that different threads would have access to disjoint set of sockets, so there would be no like conflicts, if that's what you're asking for.
I mean, can your API, implementation allow running multi-thread applications?
Multi-thread is fine.
Fine, okay. The second question I have is that, what I'm thinking is that even like the kernel spends maybe, basically kernel threads are few transition threads. They won't take many CPU resources. Basically, you're dedicating probably 1 thread per core in this case. So don't you think you are underutilizing the system resources?
At the first glance, it appears that we do exactly that. But we can, here the problem is that, say, we underutilize 1 core when the network stack is not used efficiently. Or say each of the processes of the network stack just uses a half of the core. We can use hyperthreading for better efficiency. For instance, the Niagara Spark, that would be a fantastic platform. We can also run multiple instances of network stack if we want to scale further, and so on and so forth. So there are methods how to deal with resource utilization.
Thank you.
Shin Yang from Penn State. So my question is, will this design hurt the performance of applications that do not use network? Because you are pinning the network stack on a specific core, and other applications will have fewer chance to be executed.
Why would they have fewer chance to execute?
Because
they have to share the application cores. Or yeah, this is one fewer core. Well, we're talking here about like a network server, which typically wants to use as many resources as possible. They're always hungry for resources. Or in our model, we would love to use lots of hyperthreading.
Okay.
And hyperthreading helps us to achieve the same without using an extra core. So we can share the cores and get the similar effect.
Okay, thanks.